With you, especially those students who are thinking about research in the future, is a pretty simple idea. You've heard the phrase that the devil is in the details. Well, that's really true. And a lot of times, even big questions depend on pretty small details. That if you happen to get those details right, or if you happen to find the right sources, then you can really move out. All right, that's the gist of the talk. You can go back to sleep. All right, so what do I do? Well, one of the things I do in my research is an area that's been suggested for some time, and it's called gyrochronology. Kind of a pompous word too, there's that word again. But basically it's the kind of thing that happens in any piece of history or archaeology. Oftentimes you don't think about astronomy as being the same kind of subject as historical studies or archaeology or digging up the past, but it really is. And suppose you want to find out about Mayan civilization. What you want to get are artifacts from that period. You want to see what people did for a living, how they did their work, how they did their regular lives. If you want to find about any other civilization, you need pieces of evidence from those days. Documents, trash, anything you want. Now, you've all seen Neil Tyson on television and everything else, and he talks about this kind of thing that the universe has been around for a long time, and we've pieced together that by finding stars of different ages. There are stars that we can see being made even today, and that tells us something about the process of star formation. We have stars that have been around since the earliest days of the universe, and that tells us what things were like back then. So it's a bit of an archaeology. Now, there's a problem, though, about getting ages, and this is an area that I've been thinking about most of my career, prompted by one of my advisors who would give us a case of some fine French wine if we could solve this problem. I'll outlive him, and he won't be able to give it to me. But stars do something interesting. You might not think of it when you look at the sun. You shouldn't look at the sun anyway. But stars spin on their axis the same way that the Earth does, or the moon does, or any other object. And it's an observed thing that when you get certain ages of stars, the stars spin fast when they're young and slow down as they get older. The sun, for example, spins around about every 25 days on its axis. And stars like the sun in a young star cluster, like, say the Pleiades star cluster, the Seven Sisters, when you're looking at that little clump on the sky, you're looking at stars that are only about 125 million years old. Not very long, but of course that's one tiny fraction of the age of the sun. The sun is about 4,600 million years old. So the idea is pretty simple. We might, emphasis, be able to derive a star's age from how fast it spins. If it's spinning fast, it's young. If it's spinning slow, it's old. Now, when you're constructing a research project, there's the big, lofty idea that you want to do this. I want to understand the course of Western civilization. I want to understand feminism in Northern Europe. I want to understand the rise of Inca culture. Okay, you do, don't you? Everybody wants to do stuff like that. But you can't do that just because you have the big picture. Because you have to ask yourself many, many more questions. So what I'm doing here is giving you a talk that I give to my own students when I'm recruiting them to join my research group, and to tell them why it is that especially undergraduates have to rely on my judgment, good or bad, about what constitutes a good research project. Because otherwise they'll just go off and want to investigate the whole of Western civilization or all of astrophysics instead of getting to something that's more precisely focused. So whenever you're coming up with a research question, you have to start, what do we know already? Well, we know that stars have different ages, and I'll show you why. And we also know that the young ones spin fast and the old ones spin slow. But what don't we know? What's holding us up? So I'm constantly doing this to young graduate students and everything. Why don't we know the answer to this already? I mean, why don't we know the answer to this? That's a good question. What's holding us up? What piece of information do we lack? What ability to do computations do we lack? What kind of data do we lack? I don't know. Let's try to sharpen this question a little bit up and to show you in something that's totally removed from most of your experience, astrophysics, that you do the same kind of thought processes that show up when you're studying Chaucer, when you're studying history, when you're studying any other subject. Now, the potential for being able to get ages is really, really huge. This is a big problem. This is something you want to do. And the reason why it's so big is this. Despite the fact that others, and everybody, hundreds and hundreds of stars, hundreds and hundreds of astronomers have been beavering away for a century and a half, we can determine the ages of certain kinds of stars, stars that are in star clusters, like that one there called Messier 6, number 6 in Messier's catalog of things that aren't comets. Okay, so back in the 18th century when you were looking through fuzzy, crummy telescopes, it looks like a little blob of light, like a comet does. But this is the 6th entry in something that is not a comet. Now we get the ages of stars in clusters, but it turns out that hardly any stars are in clusters. Zip. Just a tiny fraction of them, 1 out of every 100 million stars is in a star cluster. And to give even the slightest indication of what that is like, I put up a piece of the Milky Way, and it's not really dark enough to see the details, but it's beautiful with all these red stars and dust lanes and everything else. And in that little picture, there's a few 100,000 stars. And that little fleck up there is my star cluster M6. So I know the ages of just that little of stars compared to the whole shebang there, and I'd like to get them all. Because if I could get them all, then I could do archaeology of the whole galaxy. I would have a complete sample. I'd know the age of everything in there, and I could figure out how it got to be that way. We know galaxies form by gobbling up little ones, but how fast did that take place? Is most of the galaxy old? Most of the galaxy young? I don't know. I did my thesis on a little patch of light that's up there in the top middle up there, getting the ages rather indirectly of the stars in the red blob up there. They're among the oldest stars in the galaxy. This is for my PhD work. So, yeah, this would be really cool. So, not only is it an idea that's interesting, it's a really big idea. I mean, this really could, if it works, really open up a lot of stuff. Now, I'll give you reasons why it might not work later. That happens sometimes. Yeah, you got these great ideas, and maybe you can't get any kind of progress out of it after all. We shall see. So, what does rotation look like? The only star, to a first approximation, we get to see as a resolved thing, it's called, rather than a little point of light, is the sun. And you know that sun has sunspots on them. It's supposed to be elementary knowledge. But most stars, including the sun, have star spots, an analogous thing. Okay? And if you look at a sunspot group on the sun, and these are slices of images of the sun stacked up, taken in 2011 March 3 through 14, day by day. You can't see the dates, you're probably too far back, but an image of a piece of the sun stacked up day by day. You can watch these sunspot groups going around the sun because the sun is rotating. And you can figure it out that it takes about 25 days or so for the sun to complete a total circuit on its rotation. Yeah, you have to allow for the fact that during that time the Earth orbits a little bit, but you can figure that out. That's not too hard. It's not the Earth's orbit that produces this, it's the sun spinning on its axis. In a young cluster like the Pleiades, a star like this could spin around in 6 hours. So somehow it's slowed down from when it was really young to take about a month to go around instead of 6 hours. So that's an interesting piece of physics. We'd like to learn all about that. But if you're looking at faraway stars, you don't get to see the picture of this. It's still true that the star is a little bit dimmer when there's a sunspot group in front, And then the star rotates around and the sunspot group goes behind. The star gets a little brighter again. And so it's like having a light bulb with a dot on it, and you rotate the light bulb. It gets a little dimmer, a little brighter, a little dimmer. And you study stars in great precision. You find that most of them get a little brighter, a little dimmer, a little brighter, a little dimmer in some kind of more or less periodic way. And you interpret that as rotation of the stars. So it would be great if we could figure out what the relationship is between spin rate and age. Now we can do it for every star, even stars like the sun, the great majority of them that are not in clusters. So that's what rotation looks like, and it's a very hard thing to do. You take special satellites and you measure with really, really high precision what the brightness is, and they have special satellites to do that, and they're generating a bazillion of them. Now, why do stars slow down? What is it that makes it happen? It all turns out that all stars have a stellar wind that carries away mass. So the sun is leaking out a stream of stuff into faraway space. It passes by the Earth when there's a bigger blob than usual passing by the Earth. That's what gives us the northern or southern aurora, the northern lights or the southern lights. Crashes into the Earth and causes the atmosphere to glow. So it carries away mass, and it's kind of interesting. It's really, from Earth point of view, not as much as you think. Okay? So you could do the arithmetic, and you can say that the sun carries away, there's this wind is something like 10 with 23 zeros kilograms per second, or 10 with 20 zeros tons per second. That's a lot. However, it's just about as much as if you were standing on the side of the Amazon River and watching the water go by. So there are things on the Earth that move more stuff per second than the solar wind is. But here's a cartoon on this side about what happens. The stars also have a magnetic field that sticks way out into space, and as the star rotates around, the magnetic field pushes on the stellar wind and makes waves in it. It exerts a force on the solar wind particles and pushes them outwards and makes them go a little bit in a corkscrew pattern. And you might have heard from Newton, but you know from experience that for every force there's a pushback force, an equal and opposite force. If I shove on you and you shove back on me, forces always come together in pairs. And so what does that do? When you push on the wind pushes back, and that slows the star down very gradually. It takes billions of years to slow down, and you end up with stars spinning fast when they're young and slow when they're old. So maybe in order to do this, we have to understand everything about the winds of stars. Here's a picture of the sun with the wind particles coming off. Maybe, maybe not. We do want to learn that physics a little bit better. All right, let's take a deep breath. That's a lot of astronomy all at once. So when you're doing a research project, you can't just start by, I'm going to do Western civilization. You have to know a lot about what you're talking about in order to get to the next stage. The next stage is, why does some of this matter and why does some of it not matter? And this is again why knowing your subject really, really well and making sure you work closely with your advisor tells you whether you should dive in or not. Now, here's Gandalf going to the documents at Minas Tirith, right? Remember from the movie? It's even better in the book because he asks himself, wait a minute, why does the other wizard, Saruman the White, know so much about the One Ring? How did he find out? Where could he have found out? The only place he could have found out was to go to the documents that they have at Minas Tirith and figure them out. So he broke the problem into littler pieces and decided where the evidence is. I loved that when I read it in high school, because I didn't know it at the time, but I was a nerd. Whew. But I thought like a scientist even then. So these are good questions to ask about anything you're doing when you're trying to do research. What do you know already and what don't you know? Okay, so you start to say, well, I know this, that's good, and I don't know that. But obviously, what you don't know about any subject is huge. we know a lot about physics. We know a lot about astronomy. We know a lot about chemistry. We know a lot about medicine. But probably the things we don't know are even bigger. Okay? Well, that's fine. But of the things you don't know, which ones matter? Okay? And it might be that there's a lot of things I don't know, but it just doesn't matter to solving the problem. It doesn't help you figure out what the solution to the problem is. And then finally, when you get to these, of those, which ones are even possible to investigate? Okay? So, yeah, I remember I had to get corrected tonight about biblical scholarship. When you study the New Testament, you find that there's a lot of similarities between, say, Matthew and Luke. And it's been hypothesized that they both had a source called the Q document, which sayings of Jesus that they incorporated into their Gospels when they were writing it. Well, suppose it turns out that you want to study the origins of the New Testament, and you decide that you have to find the Q document in order to make any progress. Well, forget it. You're never going to find it. It's not possible to investigate it through that path. So this is why it's tricky sometimes. And of the ones that it's possible to investigate, what difference can it make between not knowing something and knowing something? Because you might find out that, I can study this, I can study that, but it's actually not important to the problem. If you're studying, for example, the powerful in any civilization, say, the Roman emperors, well, we have plenty of evidence for them because they wrote down a lot of stuff. All the news is about, in our culture, the news is about sports figures and actors and actresses and singers and, politicians maybe, and presidents get in there too, some. But, that's where all the people at the top have all the documents about them. If you want to find the everyday life of ordinary people in some civilization, there might not be very much to go on. You might not have a lot of sources that you can get at. This is why a lot of times archaeologists dig up trash and dig up discarded throwaway stuff. So in order to solve my problem, what do we need? Well, we need a whole bunch of stuff, right? We have to figure out how this works by getting stars that have both ages and spin rates. So I've been working on that for a decade or more, because that tells us how it actually works. So I worry about a star cluster of this age and how fast the stars spin, and an older one they spin more slowly, and an older one they spin more slowly. We need people to calculate how this wind stuff should work so that I can bridge between my data. And then I have to, the thing I'm worried about now, which is taking me about a year to learn, is how to do the data analysis, because it turns out that it hinges on that. It's not something you can simply do, and I'll explain briefly why that's the case. But I'm spending a year learning statistics to make sure that I can solve the problem right. So now I'm trying to break this up into pieces that require you to get stuff, and we need lots of other things too. So we already have lots of data in clusters, and remember, clusters have ages that I could figure out. So I don't need to do that. I got plenty of those. Sometimes when I was working at the National Science Foundation, that's a grant writing agency. People send in proposals. You get 15 pages, buddy, to explain why you have the coolest idea on the planet. And 90% of them get turned down. And the winners, go off and do research. But there's lots and lots of proposals that come in that says, we've been studying this for 50 years. We still don't understand what's going on. I want more data. Well, come on now. If we haven't figured it out by collecting data for 50 years, it isn't more data that's going to solve the problem. It's more calculations that's going to solve the problem, or something else. So we don't need to do that. That's not a problem. So when we were sitting around figuring this out, we wrote on the board basically something like this. We don't need that. But wait a minute, these clusters are all young. They're all less than 1 billion years old. Now the Earth's 4 billion years old, the galaxy's 12 billion years old. So, wait a minute. Here's the first part. I know what happens early, but I don't know what happens later. So I need to have at least some stars that are really old and measure their spins to tell me what it is. Well, it turns out there's a thing you can do called asteroseismology to get ages of old stars. This is really important, but it's really hard. Asteroseismology is just like Earth seismology. You might all know already that you learn about the interior of the Earth whenever there's earthquakes and these sound waves go through the Earth and cause the Earth to vibrate a little bit. And that's how you know the core is molten and it's made out of heavier material than the crust is and all this stuff. Stars like the sun vibrate every 5 minutes or so. And it's a very small vibration. The sun is almost 1 million miles in diameter, but the surface of the sun goes from about where the ceiling is to the floor, up and down every 5 minutes. We can measure that. It's little waves in the sun that are only 4 meters or so high. And that tells us what the interior of the sun is, and you can derive ages from that because the sun gets more and more dense in the middle as it gets older, and you can figure this out. So this is a really important thing to do, and we got to do that, and that's really important, but it's really, really hard. So we need lots and lots of effects to model, and I am not going to really explain what this is. I'm just going to say that when the theoreticians get together, they write down a list of things we need to know. And they have great names. Disk locking, whatever that is. This is something about the earliest phases of stars. Turns out that doesn't matter. Radial angular momentum diffusion, that's what I'm worried about now. That's important to get right. So don't worry about what it's called. Don't worry about this stuff. We're just making lists. And a thing called saturation, persistence of rapid rotation, that's really important. Okay, it's really important. So, yeah, all right. So we've gotten a list of what matters and what doesn't. Now, when you're going to be making your research programs, you're going to do the same thing. You know, it really is important to go to some primary sources to discuss, you know, I don't know, what Victorian England was like for dock workers. Well, you better find something about dock workers in Victorian England to make it happen. But you don't really need to know what the Queen Victoria felt about her gardener. You know, I mean, it's just irrelevant to that. And you have to make a list of what matters and what doesn't. So we've got these fancy names, and it turns out that there's a worry that these are all goofball stuff. Now, this is the thing that matters a lot. Now, we see when we look at these young stars that they're not all doing the same thing. I said that the sun could, a star like the sun could spin around every 6 hours when it was born, and it spins around once a month now. But even in the young systems, there's a range of rotation rates. Some stars spin faster, some stars spin slower, and so the fast ones and the slow ones all slow down, and there's a big mix of what's going on. Now, we are used to figuring out our ages by looking at each other, because on average, we all age at the same rate. You can tell a baby from a toddler, from a college student, from an old professor, pretty easy, right? I'm going to come into the light. Would anybody like to guess my age? Of course, I'm roughly a little older than your parents, but how old am I? 55. 55. Exactly. Not bad. That's better than you can do statistically, but that's all right. See, we can do it. Now, suppose we were different. Suppose some of us went through our lives faster than others. Some of us matured into men and women when we were 2, and some of them took till 50 or 60 to mature into men and women. I don't mean social maturity. Believe me, when I see some of those students at Ohio State, I know that they take a very long time to get socially mature, whatever their bodies are doing. It would be hard to figure this out. It would be much, much more difficult to figure out what the ages of individual people are because they go through this at different rates. So it could be that I could get a star that started out spinning fast but takes a month because it's really old, or maybe it was much younger and it started off more slowly and got to spinning around at a month period quicker than this first one did. So that's a complicated problem in a thing called Bayesian statistics, but you know, I'm not going to teach you Bayesian statistics. And here's the problem. Remember I said this could be really cool. This could be the start of something really, really big. Okay, there's a bunch of things that could go wrong with this. We joke about it in science, as we say that nature is not cooperating. Okay? Nature doesn't do what we want nature to do. Nature does whatever nature's going to do. Okay? Now, this will only work if stars slow down forever. Suppose they slow down to a month and then stall out and stay a month forever and ever and ever. Then you lose track of what their ages are. Right. Your precision about measuring an adult's age is a little less good than your precision about measuring, say, a 6-year-old or a teenager or something, because once you get into the adult stage, you stay there for a long time. Yeah, you know, fat, gray, bald. Certainly not 30, but hey, you're not too bad there. So hey, when we study this with all this astroseismology, we might discover that stars don't slow down forever, and that, sorry, you can't do this. Old stars might not even have star spots, so we can't measure their spin. Sorry, you can't do that either. So writing a paper that says, oh, you know that idea? Doesn't work. That too is the progress of science. We only hear about the ideas that are still alive, not the ones that are gone. You know, maybe you heard in biology that the idea that rotting meat spontaneously generates flies, right? Well, that's a reasonable idea until you conducted the experiment and you find out that it does not. What gets me going, including ranting in the car on the way home when I was frustrated about traffic, is people still believing ideas that have been scientifically discarded a long time ago. You know, I'm sorry, it's really simply true. Acupuncture doesn't work. Zip. Just don't even believe it anymore. It just doesn't. Because people did this and they said, oh, I tried an experiment and it doesn't work, et cetera, et cetera. Astrology, all sorts of other stuff. And so you might get a whole lot of nothing out of this. We might get a lot of work and a lot of everything else, and we just decide that, in fact, let's see, why am I not getting to the punchline here about the happy face? There's supposed to be one more click on here, and then it's not working. Well, big deal, I'll tell you what it is if I don't get it. The other thing we might not know is we might never know the theory of all these winds enough to make predictions, but we'll still learn a lot about stellar physics anyhow, so it works in some kind of sense. So yeah, it's perfectly all right, is it? If you start a research project that doesn't pan out because you couldn't get the sources. It's not okay to start a research project that didn't pan out because you decided to play too many video games or tweet your experience about not going to the library when you're doing your research project. Some things work and some things don't. You know, that happens. So what do? That was a complicated project. So the first thing you do is get a team together, and this is all these, what a bunch of nerds, wouldn't you say? These are all the people who are working on this particular team. Myself, Mark Pinsino, who does the theory, Savita Mathur, who worries about star spots and measuring the rotation rates, Rafael Garcia, who worries about star pulsations, Jennifer Johnson, who worries about what stars are made of, what their chemical composition is, that matter. Travis Metcalf is another guy who worries about how stars vibrate. And you go ahead and you get your resources together, and I'm proud of myself because these are two proposals, one to the National Science Foundation, one to NASA, and we scored this year, each one of which had 90% of them turned down, and you might not be able to read, what, $573,000. It's a lot of money to do these things. So we got about $1.2 million to do this project, even though we might get a whole lot of nothing about the whole point of doing this, which is to try to figure out the ages of every star in the galaxy. So the reviewers said, wow, you're going to learn a lot about stars, stellar physics, stellar winds, blah, 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 stellar ages. You really are going to learn a lot of really important stuff. But we understand that the whole point of the thing, the central idea of finding the ages of every star in the galaxy might not work. So that was really nice. And almost all of this is going to go to students, and flying out to observatories and all sorts of stuff like that. But you'll have the equivalent get your research phase, get your research resources together phase when you're building your projects. What library resources do we need? What online resources do we need? What original documents do we need? Blah, blah, blah. All right, I think that's just about it. Yep, that's just about it. So anyway, thank you, and I'm wide open for questions about science or astronomy or the philosophy of science or anything that you'd like. So anyway, thank you very much.
Let's take some time for questions.
Just a comment at this stage. You're one of the few scientists who's approached this from this direction. This is absolutely an excellent way. And the one thing you never mentioned, but was absolutely inherent in this, was the scientific method. Everybody these days in teaching science is into scientific methodology. And this absolutely encompasses everything in that. It does a very nice job.
Well, I thank you. Yes, and the thing, I considered doing that for this talk, to describe the scientific method, which is more or less come up with ideas and then test them, okay? And then throw away the ones that don't work and keep the ones that do, and maybe come up with better ideas. Now, it's interesting word test, right? So who speaks Spanish in the room? Yeah, so tell me, what is a test? Examen? Prueba? Prueba. That prueba is the same word as proof. Okay, so in mathematics, proof means to establish something beyond any doubt, but proof actually means test. And so when you have an idea, you test it against the world. And a lot of times the scientific method is presented in some kind of idealized way. And I wanted to present it a little bit more messy this time about, you start writing lists of things that matter and things that don't. Because we don't always advance hypotheses ahead of time. Sometimes we understand things only after doing all the work. Yeah, that idea would explain all of the stuff that we see. But it is inherent that you try to divide the problem up into pieces, you try to figure out which ones you can attack, and I'm building the mechanism by which I can test these kinds of things. So, anyway, great, good comment. Yes?
So when it comes to estimating a star's age through its rotation, how do you take in variables into account? Let's say, because you spoke in terms of that we know them from clusters, but what if a large body of something passed the star and that gravity causes?
That's an interesting point, because that could be yet another reason why this doesn't work actually, and it has, but we'd be able to tell. It actually wouldn't be that objects pass by the star to ruin it up, but it turns out that stars, many stars are in close binary stars. Another area I study are very close binary stars that eventually are going to merge together, but these stars orbit around one another because of their mutual gravity every 2.5 hours. So wow, that's pretty cool to watch these stars go around. In fact, they pass in front of one another and get a little brighter and dimmer, and it's kind of neat. We know when it's going to happen. You're at the telescope and well, there's going to be another eclipse at 10:15 tonight, and that could cause a big mess because most stars are in binaries and we might not be able to model that properly. But again, it's worth the chase, because if it does work, then we can get the ages of every single star, right? So I don't know how old Alpha Centauri is. It's not young, but I'd be really cool if I could tell you the age of that one, and HD 183, 143, and RU Lupi, and all these other stars around one by one, instead of the very tiny number that are in clusters.
I know a lot of times the size of the star tends to dictate how old it is, but that's not an exact science.
Well, that is true, that a star like the sun, when it gets really, really old, is going to really greatly expand. That's called a red giant phase. But that happens only in the last tiny bit, right before it dies. And the sun spends 90-odd% of its time in the phase like it is now. And it's getting those that would matter, not just what happens at the end. But yeah, the lifetime of a star is very different from ours, right? So how long does it take to make a person?
A second. A second.
I don't know. How long does it take to make a person? You might want to say 9 months, right? But how many of you guys need to have a fake ID to go buy beer, right? You're not a real person until you're 21 or so. And when you get to my age, you're starting to get too old for things. You know, people look at you like, oh, geez, you know, your parents mooching and, you know, that kind of stuff. And so, but stars are formed really, really fast and then spend their entire lives, almost all of it, except for little phases at the end in their adult phase. And so that's why this is interesting, because that's that part in the middle, except I can't even exaggerate. I mean, it would be, my arms would have to be miles wide in order to distinguish between the birth and the death phases of stars. You know, they're all long time in the middle. And that's why this, if it works, would be great leverage for all sorts of stars in most of their lifetime. Okay, so let me see a couple from the students, though. Did I stun you? Is it too late in the day? Shy in front of faculty members?
Probably a broad question, but how do you just pick out a star in the sky and know what it is?
How do we know what it is?
Yeah.
Well, that's tricky.
Which one it is?
Oh, which one it is? That's easy. That's just in a catalog. So people back in ancient times wrote down a list of all the bright stars, and they all have names. You know, Markab and Alcor and Mizar and Aldebaran and Betelgeuse and all that. But to figure out how far away they are from the Earth, what their ages are like, this is what they're made of, that's the whole subject of astrophysics. And this is why, you know, at least at Ohio State, big place, you can major in that. And yeah, I could spend 4 years telling me all about that. So, but there are techniques for figuring it out. One of the simplest ones is to get the temperature. Right? So cool stars are very, very red, and middle temperature stars are yellow, like the sun, and very, very hot stars are blue-white. And that tells you one thing about their conditions, the temperature. And you can tell their masses by how fast they orbit each other if they are in pairs. You can tell what they're made of because some of the light that's coming out it looks just like what happens to light being absorbed by iron or nickel or aluminum in the laboratory. So you look at the star and you say, oh, well, what do you know? There's iron or nickel or aluminum in this star. So there's all sorts of techniques like that to get their physical natures. Right? Yep.
Did you do any types of research projects when you were an undergrad? Like, do you remember how you came up with those ideas?
Oh, well, no, I didn't come up with these ideas. I went to somebody and I timidly knocked on the door and said, Dr. Nelson, can I help you build the Keck telescope in Hawaii, please? And he said, yeah, fill out an application to explain why you want to do that. And so yes, that's one of the undergraduate research projects I did. Same thing, there was a particular class that I did very, very well in, stuck out, and so I asked the professor, a guy named Carl Heiles, whether I could work with him, and he said, yeah, I have this new postdoc guy named Leo Blitz, work with him. And so we figured out, it was great. Oh, here's another thing that can go wrong. We spent a year and a half figuring out the conditions and the masses of the gas clouds out of which stars get made. And we were just going to write it up, and in the mail arrives a PhD thesis from the Netherlands on just that technique for just those objects. Totally scooped. So we didn't publish it, but that's okay. It taught me a lot. Yeah, so that was, that can happen.
If this works, how sensitive do you expect it to be? Margin of error?
Yeah, that's a great question. What's going to happen is that you're going to get a kind of a goofball answer, a statistical answer. So I'll be able to point at a star like Alpha Centauri, and I'll say that there's a 20% chance that it's younger than 2 billion years. There's an 80% chance that it's between 2 and 4 billion years old. And then there's another 0, because that adds up to 100, chance that it's older than that. Okay, so you get this kind of statistical estimate, which is pretty common in the physical sciences of that, So, I didn't ask you when you said, 55. I didn't ask you for a range of values, but if you had said, well, it looks like you're between 50 and 57, you're doing that kind of assessment of the probabilities. There's 0 chance that I'm 16. right? And there's hardly any chance that I'm 48. Maybe. A little prematurely gray then maybe at 48, and there's very little chance that I'm 70. So you do these kinds of estimates in your head, and you just landed on the center one, the middle of your estimate. But properly, all sorts of things have a range of numbers that you associate with them. So that's what we're going to try and figure out what it is. Now, the narrower the range, the more useful this is. But if I could say that a point at an individual star and say it's somewhere between 1 and 12 billion years old, well, that's the whole history of the whole Milky Way. That doesn't tell you anything about what it's like. And if the technique isn't better than that, isn't a lot better than that, then we don't have any real tool for that, you know. So, yeah, sure, right? Anything in Columbus is between 0 and 200 years old. That's an uninformative age indicator, right? Doesn't tell you anything about whether this building is old or that building's old or any of that. So that's why I try to make it an informative age indicator. All right, that's enough. Let's have some cookies. And if you want to ask me some individual questions, you can go ahead and do that. So thanks again.
Thanks so much.